Use a bomb to evaluate the resonance energy of benzene by Kristina Hibbeln.
The objective of this experiment is to use theoretical and experimental approaches to further understand benzene's energy resonance. Bomb calorimetry was used as an experimental technique to investigate resonance. Bomb calorimetry can be used to determine the heat of combustion of a compound. This, along with the literature values of combustion and vaporization enthalpies, can be used to quantify the experimental importance of resonance structure. Benzene is a widely used industrial chemical. Benzene is found in crude oil and is a major part of gasoline. It's used to make plastics, resins, synthetic fibers, rubber lubricants, dyes, detergents, drugs, and even pesticides. Benzene is produced naturally by volcanoes and forest fires. So anyone from a kid doing arts and crafts to a gardener or a doctor will care about resonance energy of a benzene. The first hypothesis is that the theoretical method will be the best out of all the methods used. The reasoning for this is that the bomb calorimeter portion from the experimental method plus literature values of combustion and vaporization enthalpies lead to an experimental value of the resonance energy. This implies that the experimental will acquire more sources of error when obtaining information, whereas the theoretical will acquire less sources of error. Hypothesis will be that using the bomb calorimeter for this experiment will not give high accuracy results when compared with literature values because of the differences in the heat of vaporization of the compounds of interest. This is predicted to cause inaccurate results since the bomb calorimeter measures heat of formation and combustion of these compounds of interest in the liquid phase. On the left, you are seeing the oxygen bomb calorimeter that was used for this lab. On the right, you are seeing the complete bomb calorimeter schematic and setup. The initial section is 60 seconds before the bomb was fired. The middle section is while the water is heating, and the final section is 90 seconds after the temperature stabilizes at its maximum value. Points I and A are the beginning and the end of the initial section. Points C and F are the beginning and end of the final section. Point B is at the 60% of the total temperature change, marked by the closest data point to the calculated value. The labels I, A, B, C, and F are labeled the same on all CDT and cyclohexane temperature versus time graphs, as all of them have the same general shape. Values for I, A, B, C, and F are found as described in Figure 1. Equation 1 was used to determine the change in temperature for all compounds. All calculations were done with the temperatures as measured in Celsius, and delta T values in Celsius are equivalent in kelvins. All relevant data points were used to determine the change in temperature values for each trial. The initial and final sections are approximately linear, so by using equation 1, a more accurate change in temperature value can be found compared to a simple final minus its initial equation. Equation 2 is used to determine the delta U combustion values. CDDT trials did not use a capsule. Values are used in equation 2 to determine the delta U combustion for a CDDT and cyclohexane. The heat capacity of the calorimeter values are 10,187.67 joules for the undotted calorimeter and 10,802.26 for the dotted calorimeter. QW and QWU correct for the ignition wire that is left unburned, 9.62 joules per centimeter wire. Q capsule is 3.53 kilojoules per gram, determined by the mass of the gelatin capsule. If no capsule is used, omit this term. Q sample is equivalent to delta U combustion because the bomb calorimeters have constant volumes. An example is shown in cyclohexane trial 1. Equation 3 was used to determine the delta H combustion values. The large difference between cyclohexane values is not expected, but CDT values are similar. Cyclohexane 1 value is larger than all CDT values. The H combustion values were determined with equation 3. Temperature is approximated to be constant because the overall change in temperature is small, so the average of TA and TC is used. Provided on the vaporization pressure P and temperature T for CDT, equation 4 can be used to determine delta H CDT in table 5. This data was not collected during our experiment, but the values used were measured experimentally, not computationally. For this, delta H CDT is 47,672 joules per mole. Values for P, R, and T are known, and C is a constant. The slope of the graph is equivalent to the negative value of delta H CDT. Diagraph was used to create models of benzene, cyclohexane, and CDDT. These values can be used to approximate the resonance energy of benzene using Hess's law. To determine the heat of combustion for both of these two compounds, Bohm calorimetry was used on cyclohexane and trans-cis 159-CDDT. Because of the resonance factor of benzene, Bohm calorimetry must be done on two other molecules rather than benzene directly. Bond enthalpy methods, which are used to determine many other resonance energy determinations, cannot be used in this case. Since benzene does not behave like the conceptual model and instead has all equivalent bond lengths due to resonance, using bond enthalpies will yield 0. Since the reaction of benzene and cyclohexane produces CDDT, these two were selected to find the resonance energy of benzene. Calculations can be used to determine the overall resonance energy for CDDT, which can then be subtracted to determine the resonance energy contributed exclusively by benzene. There is another way to evaluate resonance energy of benzene experimentally. In addition to Bohm calorimetry and new technologies such as skygraphs, this can be accomplished by the use of hydrogenation heat. The technique for this approach would be to equate the heat of hydrogenation of a hypothetical device of 3 separated carbon-to-carbon double bonds to that of benzene. The discrepancy between the two will be used to calculate the desired resonance energy. Calorimetry or stimulation instrument like skygraphs that can run heat of combustion numbers on its own are the best ways to truly measure or quantify resonance energy. Of course, there are sources of error in Bohm calorimetry, such as inaccurately measuring the volume of water covering the Bohm and imperfect vaporization of the neodymium wire. Since there is error in every laboratory experiment, skygraphs is the most precise way to calculate resonance energy in this field. Other processes, such as COT and bond enthalpies, would clearly not function or produce results that were significantly different from the literature recorded meaning. Compounds having a benzene ring with a minor addition can be studied using the same process. Since benzene has such a high resonance energy relative to other molecules due to its aromaticity, it is important to use these other molecules that are no longer aromatic. COT, for example, is a benzene with an additional ethylene group that is normally present in a tub shape. The heat of combustion for this molecule can be used to calculate the resonance energy of a benzene using the same procedure we used in the lab, since the anharmosity is no longer intact. Since they are fundamentally the same molecule, the resonance energy can be calculated by comparing the heat of combustion of COT minus 1 ethylene moiety to benzene. The first two molecules make sense to be pretty much equivalent because their sp2 carbons are the same, the only difference being that one of them has an extra. The more sp2 hybridized carbons, the less resonance energy there is. It also makes sense that they have less resonance energy than COT because they're not cyclic. Last, it makes sense that COT has significantly less resonance energy than benzene since it is less sterically hindered and less stable than benzene.
An improvement to this lab would be to give a set website for everyone to find literature values, since many websites differ a little. This ultimately leads to varying final data. Lastly, here are my references, and I hope you learned something new today. Thank you.